Please put your name on the attendance sheet. The game. Yes, so it's like this angry bird. We will start with problem 2.81. So we still have 2 more minutes, so you can write it down. Okay, good morning. So today I'm not going to teach any new concepts. We have learned all the basic ideas in chapter 3 related to fluid motion and Bernoulli equations. My goal is to pack as many examples as I can and answer your questions along with it. Okay. So we'll start with last lecture we did problems related to Bernoulli equation, like 2 or 3 examples. Today I want to start with focus on submerged surfaces. And one thing I'll tell you for sure is in the exam, if you have a problem on submerged surface, it will only be a rectangular plate. That is, calculate the force on a rectangular plate. I won't ask you circular, triangular, and other shapes. It isn't a big leap for you to learn those. You can learn them, but to keep the focus on just the concepts, we'll stick to the simple case of rectangle. Okay, so which is like W times dz. The area is very simple, and you don't have to do any complex integration. All right, let's do problem 2.81. We are asked to calculate what is the force on the bottom of the tank. Okay, instead of going all the way through, we'll just try to quickly reason our way through this. And if we make sure all of us understand, we can skip the numerical calculation that you can do later on your own time. Okay, so if we want the force on the bottom on the floor, what will be the what are the fluids that are causing that pressure? What are the causes? There is water of 6 inches height. Above that, there is oil also of 6 inches height. And then above that, there is atmospheric pressure. So you can say the pressure at the surface of the oil is atmospheric. And then there is 6 inches of oil, which is density times G times 6 inches. And then 6 more inches of water. So density of water times G times another 6 inches. So the pressure at the bottom would be the sum of PA plus the height due to the 6 inches of oil and then 6 inches of water. Yes?
This be an example of a problem that atmospheric pressure concrete.
Neglected? Yes, that is, if you can make the reason that Since air is like 1,000 times less dense than the other fluids, I'm ignoring it, the valid approximation. Or you can do the calculation and show that it doesn't matter even if you include it. Either way. Do we need to write it out? Are we all good? Because that's a test. If I'm able to get your approval just for a oral argument, that means we are on the same page. Do you want me to write it out?
Yeah, that'd be great.
Okay, let's do that. All right, let's do that. So here's our tank. You have two fluids, water and oil, each of 6 inches, and then there is atmospheric pressure. So the pressure at the bottom, pressure at the bottom would be P atmospheric plus the density of oil times G times 6 inches plus the density of water times G times 6 inches. Now, the reason I wrote 6 inches as it is just to show you, but what you should do is convert everything to one system of units, whether it's SI or English. Convert to, I'm going to say SI units. So you can write atmospheric pressure is like 101 kilopascals plus what is the density of oil? Specific gravity is given as
So 8.2.
0.82. So specific gravity is 0.82, which means density of oil is 0.82 times the density of water, which is 820 kilograms per meter cube. Where I assume we all know that density of water is 1,000 kilograms per meter cube. So that would be G 9.81 meter per second squared times density of water 1,000 kilograms per meter cube. It just happens that 6 inches is a common value here. So I'll write 6 inches multiplied by how many meters make an inch, or how many centimeters make an inch? 1 inch equal to 0.0254 meters. How do I know this? I just know this. So I got a very good question from one of you through email. Will we be provided conversion tables in the exam? Should I remember all of this? You will be provided. So you'll be given a sheet of all common unit conversions. You just know how to use it or what to pick out and use. Okay. So this is 0.0254 meters per 1 inch. And then I also have to write the specific gravity of oil, which is 0.82, and then specific gravity of water, which is just 1. Quick thinking, what is the unit of specific gravity? Sorry? Unitless. Good, good. So the reason I write it out like this is because you want to make sure you get the unit conversions right, and writing each quantity with its correct unit will help you keep on track. Look at this. This is 6 inches. This is how many meters per inch. So the unit inch cancels out. I have meter, I have meter, I have meter cube, right? Yeah, that's good. Yeah, so if I combine these units, I'm going to get kilogram, meter per second squared, kilogram meter per second squared divided by meter squared. What is this unit? That will be Newton per meter squared, or this is Pascal. This is Pascal, okay? This is Pascal. If you multiply all of this, you're going to end up with the unit Pascal. But in the first term, I wrote this as 101 kilopascal. So it will be better to write this as 101,000 Pascal. Now, when I was you, I asked my instructor, should I remember this number? I can't remember numbers. I'm just terrible at that. Should I remember this? I won't. So you would, just like you are asking me, I would also have to provide the atmospheric pressure value, which is, it could be an atmospheric pressure value in Memphis or Canada or Australia. The value changes from place to place. So it's not a universal value. So this will also be provided. Okay. So this conversion and this type of a value will be provided. If it isn't provided for some reason, like our friend told here, you can say it's negligible and you know that it's about this value, so it's okay to make it. So I have 101,000 Pascal plus, I have to multiply all of these, 1.82 times 0.0254 times 9.81 times 1000 Pascal. So you can take this form from here. This will be the pressure.
That would be 0.0254, right? Because you have 1.596.
Let's multiply this. 6 times 0.025. Okay. And then the force on the bottom, force on the floor would be pressure times area, and this is given as 1 square feet. Now, 1 foot is 30 centimeters. How do I know this? Well, we all have seen ruler sticks, right? You just have to remember certain things. You can't, like you see things, you have to remember some of them, right? So 1 foot is 30 centimeters or 0.3 meters. So 1 square foot is 0.09 meters squared. Sorry, 1 square. So you can complete the problem. You do the multiplication, you should get an answer in units. Are we good? Can we move on? Okay. So let's do one more problem related to forces. Okay. I think we already hit this problem. Let's see if I have something in the markets. Okay, I'm pulling out a problem from the mock exam. Three-meter wide, 8-meter high rectangular gate is located at the end of a rectangular passage. So this passage is rectangular, not circular. Okay. Rectangular passage that is connected to a large open tank filled with water. The gate is hinged at its bottom and held closed by a horizontal force Fh located at the center of the gate. The maximum value for Fh is 3,500 kilonewtons. Determine the maximum water depth above the center of the gate that can exist without the gate opening. Is the answer the same if the gate is hinged at the top? Explain. I'll give you 1 minute to gather a strategy, then we'll start. The attendance sheet going around.
Wait, for the last problem was air pressure not negligible. Like we have to use air pressure in the atmosphere.
So these values, the other terms, if you multiply, it's 10, 20 times 20 kilopascal. Yeah, it does seem important because it's only 6 inches of oil and water. So it's not, air pressure is not negligible. Okay, do we have a strategy? Have you thought of what you will do first? The question says they are already applying a force Fh, which is equal to whose maximum is 3,500 kilonewtons. Okay. The question is, will the gate stay closed for this maximum force? What is the water trying to do? Push the gate open in the clockwise direction. The force is applied at the midpoint producing a counterclockwise moment about the hinge. So you have to check whether the moment created by the water is less than or greater than 3,500. If it is greater than, then the water will open the gate. As long as it stays below 3,500, it will remain closed. Does that logic make sense to you? Yeah. So not only that. Okay, since it is hinged, it can't move. Okay, so we'll just take the moment. So now the question comes to what is the moment due to the hydrostatic force and what is the moment due to Fh? The moment due to Fh is really simple. It's simply Fh multiplied by 4 meters, the arm. Force multiplied by arm is moment. Right? So what is the moment due to the hydrostatic pressure about the hinge? That is the question you need to first answer.
2,000 Kelvin or Kelvin meter.
Okay, this is the kind of answer that I will never be able to tell if it's correct or not unless I know the logic. So you have to work out. Let's do the work. Okay. Like, are you talking about this Fh times 4? Okay. That's easy. Yeah, sure. 3,500 multiplied by 4. Yeah. Shall we calculate the moment? Yeah. Okay. System is very annoying. Camera keeps shifting.
The area of the door was 8 meters by 3 meters.
it was said a rectangular channel, okay? Was said rectangular channel whose height is 8 meters and width is 3 meters, yes. Can you draw the hydrostatic pressure distribution on the gate? You have a rectangular tank and a rectangular passage that leads to the gate, and you have a hinge and the gate is over here. Can you first draw for me the hydrostatic pressure distribution along the gauge? FH is applied at the midpoint. This is 4 meters. This is also 4 meters. Will the pressure at the top be 0, or will the pressure at the top be 0?
Top of the hinge.
Top of the gauge, or at this top of the gauge.
No.
No, because there is water all above, okay, is at a certain height. So the weight of all the water that is above this plane will show up here. So the starting pressure, we'll call it P top. Can you tell me what P top will be?
Be everything in that rectangle.
So from measured from this mid plane, the height of the liquid is given as h, and this is given as 4 meters.
GH minus 4.
Rho g h minus 4. The pressure at the top of the gate would be rho g h minus 4. Is everybody cool with that? That's the height above the plane of the top. Okay? And what will be the pressure at the bottom?
Rho GH plus 4.
Correct. The pressure at the bottom would be rho g h plus 4. And you do know that between the top and the bottom, the pressure has to change linearly with height to look like a trapezium. You know that. The pressure at any height varies linearly with z. You know this. Even if you missed the last 3 lectures, you can take it from me now. It varies linearly with z. If I tell you the pressure between 2 points is, you know, the top and the bottom, how can you write the pressure at any point C between the top and bottom? I know many of you are in my numerical methods class. We will do interpolation soon, but you have learned about straight lines and how to fit a straight line between 2 points. That's what I'm asking you to do here.
What's your question?
Sorry?
What's your question?
My question is, how can I write a simple expression for Pz as a function of height? Would be P top plus P bottom minus P top divided by the height difference between them, which is 8 meters times Z. See, I can have you memorize, or I can provide you the formula for force on a plate or moment on a plate. I hate doing that. I want you to be able to derive this from basics so that you can extend this for any shape in the future. Okay, so I'll just write it compactly as PZ equal to PT, P top plus P bottom minus P top divided by 8 meters times Z. And what is the range over which Z varies? Z varies from H minus 4 to H plus 4. You can consider this is Z equal to 0. We are interested in Z equals H minus 4 to Z equals H plus 4. Okay, so now I want to know what is the moment on the plate with respect to the hinge, which is at the bottom. It's the hinge. With me so far? Yeah? You good? Okay. Okay, before you do the hinge, let's do the more simpler pressure. Force. What is the total force on the gate? Does this expression, you look at it and it clicks with you?
Yeah.
Yeah? I take a small element. So I take a small element whose height is dz, okay, and its width comes out of the plane of the paper. So the area element is W times dz. And I do know that for this little element, I can consider the pressure to be uniform. The force on this little element is the pressure at that height multiplied by the area. And then if I want the total force, I would have to integrate over the entire height of the gate, which runs from H minus 4 to H plus 4, P of Z, W, dz. Good? Yeah. So I showed you how to quickly write the force on the gate. I want you to think and write what will be the moment of the gate. What will be dm, the moment on this differential element, if the hinge is here, okay, and remember you are measuring z from here. This is z equals h minus 4 and this is z equal to h plus 4. So you have to think z is measured from this plane. So think about what will be this distance between the center of the element and the hinge. That is the momentum. Dm equals df multiplied by the arm. So can you tell me what's the arm distance?
8.
8 minus. See, we are not only interested at this point about this point. We are interested at any. We are interested in an arbitrary point which is at a height c from the top. What is its height from the bottom? If the total height is, what is the total height?
8.
8 meters. So the arm distance will be what?
8 minus Z.
8 minus z. So the arm distance is df times 8 minus z. Yeah? Good.
you're doing it for a moment, would it not be z minus a? So that once,
The Z is measured from the top.
oh,
You go
okay,
from.
okay,
Okay.
yeah. I get it.
Alright, so now what you do is you write df is nothing but P of Z times W dz, and then you multiply that with 8 minus Z. Yes, I said.
I don't know what W is.
W is the width of the gauge that is coming out of the plane. So that's just a 3 meters number. We'll substitute at the very end.
Alright.
With me so far? Yeah. Alright, so now if I want the moment, I would have to integrate dm. That is like writing integral z equal to h minus 4 to h plus 4 w times 8 minus z times p of z dz. P of z is this linear function. Okay, P of z is P top plus, I'm just going to call this like a constant alpha because it's two known numbers divided by 8. I don't want to keep writing that, so I'm just going to call this Pt plus alpha times z. Would you be okay if I just stop now and say from here on it's algebra, you can take this home, or do you want me to continue? I can continue because there is one thing that we need to do, which is to check if this moment is lower than 3500, or for what values of h it will be lower than 3500. Okay, so we'll try to finish this. So this is going to be m equal to h minus 4 to h plus 4 w 8 minus z times pt plus alpha z dz. Okay, so this is just a little bit of integration, h minus 4 to h plus 4 w 8 minus z. I'll have to multiply this. 8 pt plus 8 alpha z minus pt z minus alpha z squared dz. Okay, so I'll write this h minus 4 to h plus 4 w times 8 pt plus z times 8 alpha minus pt minus alpha z squared dz. Can I erase this part? So this is m equal to integral h minus 4 to h plus 4 8 pt, okay, the whole divided by w 8 pt dv plus 8 pt times h minus 4 to h plus 4 dz, then plus 8 alpha minus pt times h minus 4 to h plus 4 p dv minus alpha times h minus 4 to h plus 4 c squared dz. So this is 8 pt times, what is this? H plus 4 minus h minus 4, this is again 8 plus 8 alpha minus pt divided by 2 h plus 4 whole squared minus h minus 4 whole squared minus alpha divided by 3 times h plus 4 whole cube minus h minus 4 whole cube. Plus 4 minus h minus 4. That you can see it. So this is 64 pt plus 8 alpha minus pt divided by 2. What is h plus 4 and h minus 4? What is a squared minus b squared? A plus b times a minus b. What is a plus b? 2h. A minus b is 8. So 16h. 16h. Minus alpha divided by 3. What is a cube minus b cube? Does anyone remember? Or actually, let me ask, do you remember a plus b cube? A cube plus 3a squared b plus 3ab squared plus b cube. So even if you don't, let's do this. H cube plus 3h squared times 4 plus 3h times 16 plus 64 minus h cube minus 3h squared times 4 plus 3h times 16 minus 64. If I were to drop terms, h cube goes out and the second term goes out. What do we have? 64 pt plus 8 times 8 alpha minus pt minus alpha divided by 3. I have 3h squared plus 16 multiplied by 4. That is m divided by w. So I'll take the w to the other side. What is the question? You still remember? Determine the maximum water depth h above the center of the gate that can exist without the gate opening. So it's like asking for what value of h will m equal to fh times 4 meters or 14,000 kilonewton meter. How will you solve this at this point?
plug in replace P top and P bottom with rho G minus H minus 4.
You want to plug in values, that's what it's saying,
Yeah.
right? So two situations. One is if it is classroom or you have access to a computer, there is one way to do this. If this is the exam, there's a way to do this. In the exam, you won't have a device or a computer with you. So let's talk about the exam first. In the exam, what can we do? Look at the right side. It's a quadratic in H. Okay, so you have to finally get into a form where it is like A H squared plus BH plus C equal to 0, and then apply quadratic formula to solve for H. Not pleasant, but that's what you need to do. Okay. Okay. Third, you disapprove. All right. Does everyone? I mean, you've seen quadratic equations. There are a lot of terms. PT is a known number. M is 14,000 kilonewtons meter. Okay. Alpha is a known number, meaning alpha is nothing but PV minus PT divided by 8. Okay, like you wrote here. And in fact, if you do the math, that is also rho G times 8 divided by 8, getting you only rho G. And everything else is a number. So you're going to get a quadratic equation. Okay. This will be one of those questions that said there will be one challenging problem that will push you to think further than just this class. This is the one. Okay, forget exam for a second. If this were an engineering problem you see in your senior design project or fluid thermal design course, how will you solve the problem? With a computer, meaning you have a computer in hand. That with the computer, what do you do?
I was gonna say an equation solver, but I don't even know how I'd use that.
An equation solver, fine. That is, you can program all this and it will spit out a number for you for H. Here is what I suggest you do, which will give you some useful information. The moment that kind of constrains your design is how much? 14,000 kilonewton meters, right? So if we plot the quantity M as a function of H, okay, the value that you are targeting is at a certain level, 14,000 kilonewton meter. What are the possible values of H? H has to be at least 8 meters or more. It can't be less than 8. Then that will make H minus 4 a negative number. That doesn't make sense. So H has to vary from 8 meters. I would vary this until even like 20 meters. Okay. And what do you know about the moment? It varies as the second power as H, right? So it will look something like this. Where it meets the design criteria is the value of H beyond which what will happen? The gate will open. Beyond which the gate will open in the clockwise direction. I'm sorry to break it to you. What we do in the exam is a highly artificial environment. Exams, that's why I don't put too much stock in them. They make you do something which you would never do in real life. In real life, this is what you would do. Plot the curve, meet where it reaches the 14,000 value, and read out the value of H. This will also allow you to explore additional limits on the design criteria. What if it is not 14,000? What if it is 10,000? Or you want the height to be 20, this is your constraint. How much moment should you apply? Then you know that at 20 meters, what will be the height? So you can read that out. You can do thinking in lot of different ways using a graph like this than just using an equation solver to spit out one number. Okay, so the key is visualization. You plot the two functions, that is the main function, the moment, and the value within which it should stay, and see graphically where they intersect. Which also brings us to graphical method, which we'll see on Tuesday in our numerical method. Same thing. Okay. Question? No? Is this making intuitive sense for you? Yeah? Okay. I would give 90% of the score to a student who gets here and says, this is just too complicated for me to do math. This is not a math class. And he or she puts this on the sheet and say, this is what I would do. I would totally reward them. I don't care about the last number. I care only 10% about that number. I care more about your thinking. Yeah.
So we be covering visualization on Tuesday or Thursday?
Oh, I'm saying numerical methods class. This method is called graphical method. Some of these students are also in the other class.
You said a problem like this, or a problem similar to this one will be on the exam next week.
Yes, the mock exam is supposed to give you, there will be at least one question on this type of a force on a surface.
And then to the second question of
Mock exam.
that question, because there were two
Oh,
questions.
yeah.
The position of the hinge change.
If the answer the same if the gate were hinged at the top. Answer won't be, okay, that's a yes or no question the way he has worded it, Dr. Hochstein has worded it. But if you were to solve the same problem, just if let's say in the exam, I redraw the diagram and make the hinge at the top and ask you to solve the same problem again. You are now trying to evaluate the moment. The only place where this will change is the moment is not, so the moment was dm equal to df times arm. And what is the arm now if the hinge were at the top? We previously had 8 minus z. Now what will be the moment? Why do you care about the 8 now? Because the hinge is here. The distance is measured from the hinge.
So it'd just be Z.
It will just be z, right? It will just be z if the hinge hinged at the top. I would say mission accomplished for me, meaning I'm now making you to think flexibly, not just about one problem. So until this step, everything will be same. You would rewrite this instead of 8 minus z, you will just have z. So this function will change. All this algebra, instead of this, you will have different steps of algebra, but you are still going to land up with a quadratic equation, which you might have to solve with the quadratic formula. But again, if you come here and say this is too complex, but in the real world, you clearly explain what you would do. Suppose not a quadratic, suppose this is a cubic equation. Suppose you get a cubic equation. Okay, this procedure will still work. It doesn't care whether this is a quadratic or a cubic. If it's a cubic, it will look like this. You still read out the same things from the graph. With me? Yeah? Okay. So we have 40 minutes. Let's try one more problem. Problem 2.61. I think this is also on the mock exam. So let me. Did you guys take a look at the mock exam? Yeah, everyone? Because that's the closest thing I can tell you about how the exam will look like. All right. So this is problem 2 in the mock. We just did that. Problem 1 was, we are going to do problem 1 now, inclined manometer. And then problem 3 is pitot-static tube using Bernoulli equation. Okay, we discussed this last lecture. Problem 4. Again, this is like we started doing a problem with a hole at the bottom and asking what's the flow rate through the hole because of the water that is above that level. Okay, so this is just trying to qualitatively think about what is the dependence of the exit velocity on the height of the or the depth of the hole. You can go home and try this, but what you will find is the velocity scales with square root of h. So from these 3 graphs, you have to pick out which graph qualitatively represents square root of h. This middle one, does it look like square root of h? That looks like a linear, which means it's first power of h. So either it has to be this one or this one. So you'll have to intuit whether square root of h will vary as a concave curve or a convex curve. Something to think about. And then problem 5 is measuring the flow rate. We did a similar problem last lecture. So I've given you a template for each type of problem. Okay, except this inclined manometer, which we will do now. Can you take a look, come up with a strategy, and then we'll move. So I've given you 5 problems. What I'd ask you to do is go to the book as well as the practice problems. For each type, do at least 4 or 5 problems. Totally 20 to 25 problems. Determine the new differential reading along the inclined leg of the manometer of the mercury manometer in the figure. If the pressure in 5A is decreased, okay, that wording doesn't sound right. Okay, what I would ask us to do is not worry about the worded question. We want to determine what's the pressure difference between point A and B, which are connected by 2 fluids, one of specific gravity 0.9 and another which is mercury, and then sorry, not 2, 3 fluids. First fluid, then mercury, then water. What's the pressure difference between points A and B? That's the question. Do you have a strategy how to handle the incline? There is an incline of 30 degrees. What will you do about that? Or what do you need to do about it?
All it with length cosine or length sine theta.
Can you put that without using sine and cosine? Can you say what you are doing? I think you are right. You want to calculate the height changes.
Yeah.
You want to just calculate at how much height of fluid is, how much height of each fluid is involved. You necessarily don't care about the volume of the fluid. It's about height. pressure is only about height and density. It's not about volume or area.
You don't really care about the equal, because it already gives you the vertical.
No, it doesn't give the vertical. See, yeah, okay, here it gives you the vertical, but in a way it doesn't, because here it just says the length along the pipe. So if you convert all lengths measured along the pipe to verticals, then you don't care about the angle. Okay, so let me do this on the white. Do you have the question down? The figure? Okay. All right, first we have the bulk A, and from here we have the fluid 1, whose specific gravity is 0.9, and that goes on for up to some distance. Okay, so this is 30 degrees, but this height difference between the point A and where the first fluid ends, that height difference is how much?
100.
100 millimeters. Okay, so if this is PA, okay, if this is PA, what is the pressure at this point? We call this we'll call it C, because we already have a B. What is the pressure at point C?
Oh, which is 0.9 times 1,000.
Okay, so we'll say it is equal to the pressure at point A plus the density of the first fluid multiplied by G multiplied by the height, which is, I'll call it H1. H1 is 100 millimeters. Where rho 1 is the specific gravity of fluid 1 multiplied by the density of water, which will make it 900 kilograms per meter cube. And H1 is 100 millimeters or 0.1 meters. Pressure at point C in terms of pressure at A and density and height. Okay, and then the tube continues, and this fluid is mercury. Okay, this fluid is mercury. It goes on, it takes a turn, then rises up and rises up. At some point, it is then switched to water. So until here, it's mercury. Okay, so this height here. At this plane, this is 50 millimeters. So we call this point D. From C to D, the distance is, we call it L2, 50 millimeters. And the height difference between C and D, we'll call it H2. H2 equals L2 sine 30 degrees or 25 millimeters. Sorry, not 25 millimeters, 25 times square root of 3 millimeters, which is what is 1/4 of 1.73.
I think that is 25.
Sorry. 1/4 of 1.73 is not 0.5.
Sine of 30.
Oh, okay, fine. I thought sine 30 was half. Sine 30 is 0.5, which is 25 millimeters. That's correct. So 50 times half, which gets us 25 millimeters. Trust me, I used to be smart. So can you tell me what is the pressure at point D? If the height difference between C and D is H2, what is the pressure at point D? That will be Pc plus density of mercury times G times H2. Density of mercury is equal to the specific gravity of mercury times density of water, which is 13,600 kilograms per meter cube, and H2 is 0.5 meters. Sorry, not 0.5 meters, 50 millimeters, which is 0.05 meters. Okay, with me? Yeah. So if this is point D, okay, and we label the point, 1 second, we label this point as E. What is your question?
H2 should be 0.025 meters, right?
Sorry, 0.02. Right. Correct. Thank you. Okay, if we label a point E, which is at the same plane as D and is connected by mercury from D to E, what is the pressure at E? Same as whatever is at D, right? So the next point in our list is PE is equal to PD. Okay, and then we have water. We have a column of water, and then the tube takes a turn, and the point B is at this level, and we have a bulb or a tube. So this is water. So how do you write the pressure at point B in terms of what is the pressure at point E? What is our always we say about pressure? It increases if you go along with gravity and decreases if you go against gravity. So this must be PE minus density of water times G, and this height we'll call H3 times H3. Density of water famously known, H3 according to the figure 80 millimeters. So even though this is a inclined manometer problem, the only time we use the angle was to compute the height difference between 2 points. Otherwise, it's a regular manometer problem. Yeah.
So if a problem like this, would we just be given the pressure at A and find pressure at B?
That way, or asked for, right now I am asking you for what's PB minus PA or PA minus PB. The wording will be what is the pressure difference between the two limbs, or what's the pressure difference between A and B or B and A or something like that.
Okay.
So you come up to here. You just have to eliminate intermediate points to express the pressure difference. The pressure difference PA minus PB in terms of known quantities. That's what calculating means, right? If you write PA minus PB equal to everything else, you compute that. Can you take this home from here? Can I move on to the next problem? Okay. To do more flow rate problems. I don't know. Oh. All right. Okay, problem 3.75. Actually, we'll do problem 3.76. It's a more interesting exam. 3.76. So we still have 20 minutes. Hopefully we can pack one example. So if you watch this lecture and last lecture's recording, you have solution for all 5 types of questions on the mark exam. Okay. All right, problem 3.76. The specific gravity of the manometer fluid in this figure is 1.07. Determine the volume flow rate. Okay, so here is the problem or the sketch. Determine the volume flow rate Q. If you have, let's say, a fluid that's coming through, it could be water, gasoline, or air. You have here a way for the fluid to get in, and you are then measuring a pressure difference. Okay, you are asked to calculate Q. Now, before you do anything, the fluid goes in here and is brought to rest, and the fluid travels across, and this hole is drilled perpendicular to the flow. So what pressure is felt here, and what component of the pressure is felt here? What is felt on the right side, which is at a depth of 20 millimeters below the left side? On the right side, you are saying it's dynamic pressure. Okay. Anyone else? So the fluid goes in and is brought to rest completely on the right side. And on the left side, the fluid is not directly captured or brought to rest. It just flows past it, but the static component is going to be sensed in the perpendicular direction. So what component of the pressure is felt here, and what component is felt here?
Pressure on the right, static pressure.
Total pressure on the right and static pressure on the left. Okay, so we are asked to calculate Q. Don't be sidetracked by that. You are asked for Q, you are told the diameter of the cross section area. It means they are really asking you to calculate the velocity and then multiply by the cross section to get flow rate. So it's a velocity calculation problem. It's a classic use of pitot tube for velocity measurement. Okay, so first is the flow is assumed inviscid, meaning we don't consider viscous effects, and we also think it's incompressible, which means we implicitly think it's a low speed flow. And then we are asked to do the same calculation for water, gasoline, air. That's beside the point. If you are able to set up the main equation and get it in terms of density of the incoming fluid, then you vary the density to get the flow rate for air, gasoline, water, any other. Can we do that? If you know the pitot tube equation, it's very easy. You can just write that equation and move on. If you don't know, I'll show you quickly how to get there without memorizing anything. Are we good? Can we move? Okay. So here is our pipe where you have mounted the first probe that collects all of the fluid and then brings it to the manometer. And then you have the second hole where it is drilled perpendicular to the pipe, and that is connected to the other limb of the manometer. So if the fluid here has to be above this level. This would be the height difference, right? The static pressure is always lower than the stagnation or total pressure. So this would be P static. This would be P total. With me so far? Are you okay? So P total minus P static is equal to density of the manometer fluid times G times the height in the manometer, the height difference. Good? Yeah? Okay, so now we need a connection between rho mgh and the velocity of the flow so that you can actually calculate it. And this connection is provided by Bernoulli equation. This connection is provided by Bernoulli equation. So I'll select the point here and call it 1. That streamline terminates at the surface, and I'll call this point 2. So P1 plus half rho V1 squared equal to P2 plus half rho V2 squared. Density is constant because we are told the fluid is incompressible. Okay, what is P1 or what is the static pressure at 1? Actually, I should draw one somewhere here at this plane, so that the static pressure is felt here and the stagnation pressure is felt here. So P1 equal to the static pressure at 1, which is read by the PS or the left limb. V1 is the velocity that we are trying to solve for. And P2 is the stagnation or total pressure at 2, and this is PT, the right length. And what is V2? What is the velocity at point 2? 0, because the fluid has been brought to rest. Fluid at rest. It's been decelerated from V to 0. Okay, so you put that in. PS plus half rho V squared equal to PT plus half rho times 0. So PT minus PS equal to half rho V squared. That's the connection, which is also equal to the density of the manometer fluid times G times H, which means if I want the velocity, that will be 2 times density of manometer times the density of the fluid multiplied by GH squared. And if you want flow rate Q equal to VA, which is square root of 2 times rho m over rho GH multiplied by area of cross section pi d squared over 4. Where d is the diameter of the pipe. Yeah,
Is rho and the density of mercury.
density of the manometer fluid, correct. Okay. So if you think about not just the formula for velocity, just think a little bit about what are the requirements on the manometer fluid. Requirements on the manometer fluid. What all should it be like? What all it should not be like? If the manometer fluid and the fluid that you're trying to measure, if they are one and the same, would this work?
No.
It won't work. So it has to be very different. Very different from the fluid that we are trying to measure. And the fluid being measured. If it's air, it can't be air. In fact, air is a very terrible manometer fluid for a reason I'll tell now. If your flow is water, you can't have water because it will just mix. Okay. So then what is the requirement? It can't be the same. It has to be different. In what aspects must it be different?
Density.
Density has to be distinct. The density of manometer fluid must be greater than the fluid being measured. Not only it's about density, what else? What if you have let's say this is water, okay? And the fluid you are trying to measure is carbon dioxide. What is the problem? It will just dissolve in the water and start vanishing from the flow. It's like a siphon. Basically, it can soak up CO2 and turn into soda, where your the pressure reading will not reflect. So the other requirement is they have to be immiscible and insoluble in each other. You can't have them mix and form a new solution. They have to be immiscible. Okay. Let's say you take the manometer fluid to be water or mercury. You've seen manometers, right, in the fluids lab, in other places. Anywhere, have you seen a manometer with mercury? Most of you know. Okay, we'll have to figure out a way where we can see it. Maybe we can do some internet search. But the most commonly used manometer fluid is mercury. And one place where you can definitely see this next time if you go to a doctor, are asked to look for their blood pressure cuff, which they do the old school way, where they have a column of mercury and the mercury will rise up and then fall down as they take your blood pressure. Why mercury? Why is it so common?
It's very dense.
Sorry?
It's very dense.
It's very dense. It's not only very dense, it is also immiscible. It is not only immiscible, it has very low vapor pressure. So the other criterion is low vapor pressure. Why does that matter? Let's say you use instead of water or mercury, let's say you use gasoline as your manometer fluid. What will happen if you use gasoline, which is very volatile? It will evaporate, it will turn into vapor, it will mix with your flow, and you will smell the gasoline downstream, which is not what you really want, right? So you have to have a fluid that is very dense, not miscible, or it doesn't mix with the gas that you're trying to measure, and has to have very low vapor pressure. And mercury happens to be one of the fluids that check all the boxes. Water does, but water can evaporate significantly, so water is not very good. Okay. It also has to be chemically passive, which also is actually satisfied by mercury. It doesn't react very easily. It doesn't oxidize. It doesn't turn into a compound that easily. Thank God for mercury. There is no other material that is actually like mercury, which can fit all the boxes.
What about gallium?
Gallium?
Yeah.
Maybe, but I don't know if gallium is as commonly available as mercury. So I also have to think about.
So what I know is similar. It has a slightly higher melting point, so it doesn't melt below room temperature. I think it's slightly above at
Is
like,
it a liquid?
is liquid at, I believe, like 75 or
30
80
degrees.
degrees Fahrenheit.
Well, room temperature is not that. I mean,
Well, that's what I'm saying, it's slightly above room temperature.
Yeah. Gallon's
so
the same point.
okay. If you look at historically, mercury has been used mainly because it's liquid in most of the temperatures that we do care about, and it's always liquid. I don't even know what's the freezing point of mercury, and it has very low. In fact, it's a very low vapor pressure bit that's most important because I don't know about gallium, but if it keeps evaporating, you will lose your liquid. Your measurements are all screwed up.
Well, that's what I was gonna say, is I know gallium doesn't have. I know it doesn't evaporate like mercury as well, but it doesn't have toxicity problems like mercury does.
I'll say one thing. I'm not an expert on why mercury, but I know post fact that it has all these good features.
Yeah.
If I see more gallium thermometer pressure gauges in the market, I'll know why they went with gallium. I can maybe understand that. But for me, it seems like a good choice, or these are the ideal characteristics, most of which are satisfied by mercury. Okay. All right. So we have 2-3 minutes. Questions about the exam.
4 or 5 questions.
5.
Five.
20 points each.
One of them only is gonna be hard.
I never used the word hard. I said challenging.
Challenge.
Two of them will be reasonably easy. If you paid any attention at all, you should be able to get them. 2 of them will be average difficulty, where if you showed up for class and went through the discussion, some of those will be things I said in class. And 1 of them will be challenging.
Yeah, one sheet of cheat paper, is it only one side?
Okay, you can bring any number of sheets of handwritten notes,
Do you bring a notebook?
any number of sheets of handwritten notes, no printed material. It has to be your handwriting, you can bring. No printed material, no devices. Make sense? Oh, you want to bring your entire notebook? Okay, I can't allow that.
Wait, actually,
What number of sheets do you think is reasonable?
2,
2 sheets, all sides.
3?
2 sheets,
2 or 3.
2 sheets, 4 sides. That's it. No more.
Bro.
Two sheets, 4 sides, no more. Okay? Any other question? Yeah,
I can't print off my notes from my iPad.
I look at your handwriting. If it's your handwriting, I'll allow it. If it's a printed material like a textbook, I won't allow. Bring a calculator. Okay? And please arrive on time. We want to get started at 11:20. Yes. Okay, thank you. Good luck. Yeah.
Three questions. One, you said that if we have a question that requires atmospheric pressure, you will give us atmospheric pressure.
Yes, I will provide. You can assume, if I don't provide, you can assume reasonable values or make some assumption and go with science.
Okay, your office hours are Thursday and Friday,
But Friday by appointment and Tuesday, Thursday at 1:30.
Tuesday, Thursday, Wednesday. Okay.
But not today. Today